eigenvalues, and that's a consequence of the fact that the potential is of Coulomb, Coulomb, French, Coulomb, probably, yeah, French, I think, physicist. The Coulomb potential is what you get, for example, when you have if you have a charge here, and the potential at some other point here will depend only on the distance. So basically, some constant, effectively, divided by the distance. That's the Coulomb potential, right? And this degeneracy that I've been talking about is just a consequence of the fact that for this central potential that we're talking about, this whole chapter, this short chapter, is of this form, the Coulomb form, right? Now, with other potentials, not of Coulomb form, not of this type, this degeneracy disappears because the energy eigenvalues, I assume, will have L's in them, right? So this is a kind of special case. It's a bit accidental, put in commas, as a result of the potential having Coulomb form. In other words, it's some constant divided by the distance to the source of the potential. Like the hydrogen atom, that source would be the nucleus, the single proton in the nucleus. All right. So what we've done now is we've found the eigenvalues, okay, for the energy. Now, next step is still solving eigenequations, basic notion in quantum mechanics. So next step is to find the eigenfunctions, right? Now, so we go back to here. Our plus circle equation here. So we now need to solve this to find what the F are. Now remember, we assumed the F are a weighted sum of powers of rho. Okay, so we now need to solve this fully. We need to know what all these coefficients are. We only dealt with one of them to get the eigenfunctions, to get this restriction. Right? We knew lambda had to be of this form, integer form. Right? So we now need to know what the coefficients are here in full to know what F is. Okay. Now. Something's a little bit. Now, see, we've done this kind of thing before. Assuming some function is equal to, represented by a weighted sum of powers of some variable. We've done that before, but what's new in this case is and you may ask why. Well, usual answer, it works. What's new here is we're going to assume that these powers of rho have a lowest power, and below that the coefficient here is 0 in effect. So these rows, so it won't be like some constant plus some coefficient to n being 0. And then rho to power 1, and then rho plus to power 2 and 3. We're going to assume that there's these powers start at some integer low value, but the earlier smaller powers here, smaller values of n, they're not there. So that's new. We're going to assume that this weighted sum starts at some value of n here, be small, but not 0, and maybe it's not 1, or maybe not 2. It's going to start at some integer, but not at the bottom, so to speak. So, to give you a concrete example, it might be you might start at n as 2, so you'd have like this weighted sum will be A2 rho 2 plus A3 rho 3 and so on. Okay, we're going to assume that there's the smallest n, right? So that's why I've underlined here twice to make sure you remember it. Okay, so assume that the lowest power here is k. So the value of n is k. That's the lowest power you can have in this weighted sum. Alright? Alright? So assume that's true. So again, plug in, substitute, put this, which is f, put it into the equation again. So this one, right? Plus circle, and have a look at the coefficient. Have a look at the coefficient of what you get when you put this into this. Then have a look at the coefficient of which power to the lowest power of what you get, and it'll be k minus 2, the lowest power. Right? Now why? And since all these coefficients have to be 0, this term here, which is the coefficient of this lowest power, will be 0. Now I've written it out in full in the textbook. It's sort of condensed a bit, but I'll derive this term for you now. So perhaps I'll go through again, try to clarify what we're doing. So you plug in this form into this equation, right? You then look at the coefficient of the power of rho with the smallest power here, the smallest, okay, that results from this equation, okay, and have a look at that coefficient. That coefficient will be this here. Now, where does that come from? So now I'll show you where it comes from. Okay, so you got a k times k minus 1. Where does that come from? That comes from here, right? Now, your f will have a smallest term, which we agreed would be k, right? That's the lowest term. And we're trying to find the coefficient of the rho with the smallest power after you've done all the differentiating in this equation. And that smallest power will be k minus 2. And so if you differentiate twice, so if you differentiate, the rho to the k will become k rho to power k minus 1. Differentiate again, so you get k times k minus 1 times rho to power k minus 2. Okay? So here's this term. So this k times k minus 1 results from this differentiating twice. Okay, now have a look at this one. This will give you k times rho to power k minus 1, but you've got a 2 here, and you're dividing by rho, so you'll get a 2 times k rho to power k minus 2. K minus 1 from this divided by rho. Okay? So you get a 2k from there. That's this term here, 2k, right? And you'll get another term from here, because you're dividing by rho squared. Okay? Now f will have maximum power rho to the k, and you're dividing by rho squared, so it'll be k minus 2. Okay? So, but it's minus. So that's where this comes from. So you'll have k times k minus 1 plus 2k minus L into L plus 1, okay? Which is this here. And that whole thing, since it's the coefficient of this, has to be 0, okay? Now, in the textbook, this 2k is not here, but you do have a plus here, k into k plus 1, which is pretty obvious. right? So that means this coefficient is k times k plus 1 minus L into L plus 1, right? And therefore k times k plus 1 equals L into L plus 1. And that will put restrictions on what possible values your k can have, right? Because assume we know what L is. So now we have restrictions on what k can be. Now another point, this coefficient here doesn't get cancelled by contributions from other powers of this sort, because there aren't any others. There aren't any other powers of this, right? Because why? Because we chose k to be the lowest power resulting from this. Okay, so there is no other contribution, other contributions to this coefficient here from this, because k was the lowest power. Okay? There just aren't. This is it. This is the lowest. This is the lowest term for the lowest power of rho that results from calculating all this. Okay. Therefore, this must be 0. Okay. And well, it's next session, but so that implies that as I was just saying before, k times k plus 1 has to equal L times L plus 1, and hence you can solve for k.